So this is the problem, is that GPS is a legacy kind of network and we haven't upgraded it. So how are you solving this? Is it in your email? It said Zyros. I've been calling it zeros, but it's Zyros.
Zeros is, yeah, that's how we pronounce it. Awesome.
Okay. So how are you solving this using quantum clock synchronization? How is this the solution?
Yeah, so this is a fairly well-known problem. My co-founder, who came out of the Office of Naval Research, knew that this was a problem. He was a quantum scientist, and in 2018, he invented quantum clock synchronization using relatively standard quantum optical hardware. And it started, like every great breakthrough technology, as an idea. He wrote a paper. There was some hardware in the lab, so we decided to demonstrate it, test it out in a lab environment. Lo and behold, it had a level of accuracy that was very impressive, down to picoseconds.
Mhm.
And again, picosecond, 1 picosecond is 1/1000th of a nanosecond. GPS is accurate to roughly, with very good equipment, 40 nanoseconds. So getting down to picoseconds, that's 3 orders of magnitude better, more accurate. And so he patented it. We formed the company around this in 2019. And since we've gotten some US government contracts and are now architecting that system to replace GPS with a focus on the timing at first. Timing is the easiest market to address and the simplest to develop. So we're going to start off with providing that enterprise timing system for networks and telecommunications.
Okay. How how does that work? How does quantum clock synchronization work?
Yeah. So, when I mentioned GPS, it has what they call a one-way time transfer system over RF. So our system is using that optical quantum link for very accurate two-way time transfer. And the way it works is it's fundamentally, it's quantum, so it sounds very exotic.
Yeah, it's a quantum's like a bad marketing term at this point.
Yeah.
And makes me skeptical of anything.
Yeah. Agreed. We gotta kind of peel back the hype from the reality.
Mhm.
So our system is essentially a laser. Most laser communications, optical communication systems work by taking a laser and pulsing it on and off very rapidly. And that's how you move zeros and ones at a very, very high data rate. And that's been around forever. Quantum communications, it also uses a laser, but you're turning down the power on the laser so that you get a stream of particles of light called photons. And there's been methods out there for a few decades on converting those photons into pairs of photons that are entangled. So you get a blue laser going in and you get a pair of entangled red photons coming out,
At the receiver.
just coming out of your box, out of your transmitter,
Okay. So out of the satellite.
out of the cell.
Out of the
Yeah.
satellite, you have a blue light and then it turns into two red.
Yeah. So and then so for all intents and purposes, you got a stream of, you know, two red lasers, but the photons, the important part is they're quantumly entangled
Okay.
and they share the same information because of the magic of entanglement. And I can send you one of the photons. I can receive one of the photons. Normally, this has been used for, we can both measure our photons, and because they share information, we could create a string of random bits that we use for encryption keys. This is what is known as quantum key distribution. And QKD was invented 30 years ago, so that's kind of old hat. What my co-founder recognized too is that, well, those photons, you can measure it with your clock. I can measure my photon with my clock. Our clocks are offset. We don't know how much, but we know they're not aligned. And we can use that to figure out that offset between our clocks to a very, very high level of accuracy.
Mm.
And that's at a high level how it works. And like I said, it's orders of magnitude more accurate than what you can get with it. And definitely a lot more secure because you are dealing with entangled photons, it can't be jammed or spoofed the way RF can.
because if one of them's different, you'll notice something is different. So they have to spoof both of them. When you shoot the photons from the satellite, do you know which receivers they're going to? Like you can kind of target them to different receivers.
Yeah. Yeah. The technology out there, that's fairly straightforward to do. Yeah.
Okay. So you target them to specific receivers and then you can tell the difference. So then you can't actually spoof. They didn't. Can you spoof both of them or
No, not, there's still work we got to do on the security proof, but fundamentally, no.
okay.
You think of RF, RF is just a broad, electromagnetic, spectrum that goes out. So that's why it makes really RF receivers are fairly omnidirectional and can be overpowered fairly easily. Just in general, an optical link is point to point, and which right there makes it hard for somebody to insert themselves in the middle and, confuse you. But then you have the entanglement piece on top of that. And we can put some protocols in place to say, you're getting the link from me and me only. There's no fake man in the middle that can make you think you're getting a signal from anybody other than me.
Okay. And then why is it faster if both of them are using lasers?
Well, just fundamentally, you're saying why is it more accurate?
Yeah, you were saying it was to the nanoseconds or to the picoseconds instead of nanoseconds.
Yeah, so there are a number of reasons why you got a limitation on the accuracy you get from RF. There's a kind of a stack of reasons, but part of it is just losses associated with RF signal. You get some multipath, you get some kind of effects like that. And also just the accuracy of, how you get the signal itself from the satellite or the source. It kind of gets a bit into the weeds, but
I'm totally
one of the magic things about is those two photons are created at they're created at the same time, right? They have the same time reference at the time of creation. So, I can send one to me and I send one to you. They're both, we know that every photon is kind of starting with that very exact same time reference, which is part of the reason that in theory, you can really get very high levels of accuracy synchronizing our clocks, which are off from each other.
Okay. So you have them starting at the same time. And then once they're received, then they check that time and then you can check it to a higher order of accuracy, magnitude of accuracy. Okay. So it's like kind of done on the back end afterwards.
Yep.
So it's not like real time. Okay. Okay. Cool.
Well, and we're working on the system, so it will be real time. I send you the photons, and it's near real time. That hey, with it, our goal here is that we establish the link between the two of us, and within a few seconds, tens of seconds, we got our clocks, synced up immediately. So it's just a quick, I zap you, and the synchronization happens very accurately and very rapidly.
Okay.
So, yeah.
Yo, what's up, everyone? I hope you guys enjoyed that clip. I have more clips on the channel, and the full podcast is linked in the description. And I got some more cool interviews coming soon. So I'll see you guys in the future. Peace.